Welcome to today's class. Today I'm going to speak about SU11, which is another incarnation of SL2R. I'm going to introduce it as a matrixly group. Then I'm going to characterize explicitly the matrices that belong to it, the entries of the matrices that belong to it. And then finally, I'm going to show that SU11 consists precisely of the matrices in the SL2C whose associated Möbius transformations preserve bijectively the open unit disk. I'm going to do so by showing that SU11 is conjugate inside SL2C to SL2R. So that's going to be the key argument. Okay, so we saw last class that the 2x2 matrices with complex entries and determinant 1, whose associated Möbius transformations preserve the upper half plane bijectively, are precisely those 2x2 complex matrices of determinant 1 whose entries are actually all real. So here, when I emphasize that those are Möbius transformations that preserve U bijectively, I emphasize it so that one doesn't get confused into thinking that we consider all Möbius transformations such that mu A of U is contained in U, so that U is preserved. I emphasize it so that we know that we are requiring that the preservation is bijective, so that not only does this hold, but actually one has equality. So why? Because it is very easy to give examples of Möbius transformations that satisfy this, but don't satisfy this, and hence actually A does not belong to SL2R. So the condition for belonging to SL2R is that one has not only inclusion here, but actually equality. Okay, so that's why I emphasize this preserve U bijectively. Now, U is a disk in C bar, right? It's a connected component of the complement of a circle in C bar, namely R bar, which is R union infinity. So whenever I take any group of Möbius transformations, so any subgroup of mod plus C bar, consisting of Möbius transformations that preserve any given disk, one should expect that group of Möbius transformations to be naturally isomorphic to PSL2R, right? Because one would only need to conjugate in mod plus C bar by a Möbius transformation that takes bijectively the given disk onto U, or vice versa, right? U onto that disk. So what I'm trying to say is that PSL2R is the prototypical subgroup of mod plus C, consisting of Möbius transformations that preserve a disk. All Möbius transformations that preserve a disk. So it's the prototypical example. Any other example should be isomorphic to PSL2R. Okay, so today we are going to see one such subgroup of mod plus C bar, different from PSL2R. By looking at another disk, not U, but the unit disk. So let me introduce the group as a group of matrices, namely SU11 is defined to be the subgroup of SL2R, or SL2C, I'm sorry, SL2C, consisting of all those matrices that preserve this the bilinear form of signature 1 minus 1, right? And when I say preserve, is that what I mean is that A times that matrix of signature 1 minus 1 times the complex conjugate of A is the conjugate transpose of A is the matrix to be preserved, right? So A times that matrix times the conjugate transpose of A is this matrix. So here you see A star is the conjugate transpose of A. Okay, so that's a definition typical of when one defines a matrix Lie group, right, as a group of matrices that preserve certain bilinear form. The bilinear form, of course, encoded into in a single matrix. Okay, and now we would like to characterize explicitly the elements of SU11. Or more specifically, we would like to see how, if you give me such an A, what can I say about its entries, right? And what one can say is that, well, of course, it still has determinant 1, but the entries, what happens is that one can say that the second row can be obtained from the first row by switching and conjugating, right? So that's the characterization, right? Now here, notice that this tells me that as a real Lie group, it has dimension 3, because somehow what I get is, okay, the second row is all fully determined by the first row, and in the first row I have 4 real parameters, right? But actually one of the parameters can be put in terms of the remaining 3. So this is a Lie group of dimension 3. Of course, this discussion on the dimensions of SU11 is kind of, it's not very formal, but we should expect it to have dimension 3, right? Just like SL2R has dimension 3, right? Because it has 4 real parameters, but the condition that the determinant is 1 says that actually you only have 3 free real parameters. Okay. The proof of this lemma is kind of basic computations. So let's go through the proof that this is the characterization of the elements of SU11. So now for such a matrix, if you give me a matrix, then by definition it has determinant 1, and since it preserves this bilinear form, when we perform this product, obtaining this, we can deduce that this is 1, this is minus 1, and these two are 0, right? So this equal to 0, this equal to 0, but notice that this is the conjugate of this. So this equal to 0 and this equal to 0 can be written in a single condition. Now, this equal to 1 is, of course, this difference of norms to be equal to 1. This equal to minus 1 tells me that the norm of delta, the square norm of delta minus the square norm of gamma is equal to 1. Also, from this condition, we see that the square of the norm of alpha is 1 plus something non-negative. So this cannot be 0, right? It's at least 1 always, so it cannot be 0. So alpha cannot be 0, and similarly delta cannot be 0. Okay, so since delta cannot be 0, delta conjugate cannot be 0 either. And from here, then we can solve for beta, right? So I pass this to the right. So beta is this quotient. Okay, fairly easy. Now I plug in this beta into the determinant condition, and when I substitute that, I obtain this equality, and then I can multiply by the denominator, which is delta conjugate, right? And so what I obtain is, you see here, delta conjugate becomes the square of the norm of delta. Here I have the square of the norm of gamma, and on the right I get delta conjugate. Right now, here I have alpha as common factor, so I factor it, and then I realize that this was equal to 1. Right, so this gives me alpha, and so I deduce that alpha is delta conjugate. Alpha is delta conjugate, so I'm in on the right track, because here you see I was asserting that this one was the conjugate of alpha. And that's what I just got, right? That this one is the conjugate of alpha. That's what I just obtained here. Now, now I recall this equality, and from that equality, you see alpha and delta conjugate are the same, so they cancel. And I obtain beta equal to gamma conjugate. So I obtain that this is the conjugate of beta. So I write it. And A always had a determinant 1, right? But when you take the determinant, you obtain precisely the norm of alpha square minus the norm of beta square, and that is equal to 1. Okay, so this means that so far what we have shown is this inclusion, that every element of SU11 has the desired form. But on the other hand, you see, if you take any matrix here, and you just plug into here, into this, you just perform this operation, you obtain what you want. So the other inclusion is just obvious, right? It's straightforward. Okay, so now we have a more concrete grasp of SU11. Okay, and next, as I said before, I'm going to focus on proving that it's precisely the group of complex matrices of determinant 1 whose associated Möbius transformations preserve the open unit disk, which I'm going to denote by this D, right? So some sort of math BB capital D. Okay, now both U and D are disks in C bar. So there must be at least a Möbius transformation sending one to the other, right? Because of the transitivity in triples, right? And because circles go to circles. I mean, something I can do to send one to the other with a Möbius transformation is look at the circle which is the boundary of U, namely R bar. Look at the circle which is boundary of D, namely the unit circle. Take 3 points in R bar. Take 3 points in S1. Just carefully arranged so that for instance, so that let's say going counterclockwise inside U, following those 3 points, corresponds to going counterclockwise on the circle following those 3 points, so that indeed U is mapped onto this, right? And then once I have those two triples, the triple in R bar and the triple in S1, then just compute a matrix whose Möbius transformation sends ones to the other, right? And this tells me that there must be plenty of Möbius transformations that send bijectively U onto D. Right? So I'm going to fix ideas, and I'm going to take a Möbius transformations that sends -1, 0, 1 to the triple I -1 I. So you see here when in U I follow the counterclockwise sense. I go -1, 0, 1, and here I follow the counterclockwise sense. I follow I -1 -I. Right. So the Möbius transformation that takes -1 to I, 0 to -1, and 1 to -I, indeed sends U, the upper half plane, onto the open unit disk. Okay. Now, how to find it? Well, I mean, one can just start playing with some arithmetic games, right? Like for instance, first send this to 0, 1, infinity, let's say, and then 0, 1, infinity to I -1 -I, right? Both things we know how to do explicitly, and then take the product of the matrices that we obtain, right? For instance, that's one thing, and then one arrives at a non-zero complex multiple of this matrix, right? Now, in any case, if I just give you the matrix and then you plug in you evaluate in -1, in 0, and 1, then you directly see that this one has the desired properties. Okay. Right. By the way, this Möbius transformation, is often referred to as the Cayley transformation. The Cayley-Möbius transformation. Okay, and what by construction, it sends bijectively and biholomorphically U onto D. Right, so it's a biholomorphism between U and D, and it's a biholomorphism given as a Möbius transformation. Right, so it has all possible nice properties. Right, it's a biholomorphism and it's actually a Möbius transformation. Okay. An exercise, right? What if what if one takes other points, right? to determine all Möbius transformations that send bijectively U onto D, it's enough. One can always fix these 3 points, and it's enough to put these 3 points to vary. To vary, of course, always following the counterclockwise sense, because here it's followed this way. Okay. All right. And the claim, the exercise, says that once you have one Möbius transformation that does the job, you can obtain all the others by simply multiplying the given matrix, the Cayley matrix with any element of SL2R on the right, or composing the given Möbius transformation with mu A for mu A running arbitrarily, for A running arbitrarily in SL2R. So exercise 4 determines explicitly all the Möbius transformations that send U bijectively onto D. And here again, see, this is a 3-dimensional manifold, and so actually one has it's like a 3-dimensional subgroup. This is well, I'm not going to say more, but the fact that this is 3-dimensional and SL2R is 3-dimensional, and SU11 is 3-dimensional over the reals, it's no coincidence. It's the same 3 in all the places. Okay, and now the theorem, which is that the theorem we proved for SL2R and for the preservation of U, but now for D, right? So for a matrix of determinant 1, for a 2x2 matrix with complex entries and determinant 1, it is equivalent that it preserves D bijectively, right? That it preserves V bar bijectively, so the closed disk of norm of radius 1, that it preserves D and also the boundary, and that it belongs, that the matrix that determines that Möbius transformation belongs to SU11, right? And now, of course, one thing I could do is go through the same with the same strategy as I did with SL2R, which was like show this, and this, right? And I could, but I'm going to rely on the fact that the corresponding theorem for SL2R and U is already proved, right? So I'm going to rely on the fact that I already have this theorem here proved to just rely on a shorter argument. So because we already know that the theorem is true for SL2R and U instead of SU11 and D, to prove this theorem for SU11 and D, it suffices to show that SU11 and SL2R are conjugate inside SL2C. And I give you as an exercise to produce the argument as to why the fact that these two groups be conjugate implies the theorem. Okay, Okay, and that's what I'm going to do. I'm going to prove that they are conjugate in SL2C. I mean, also in GL2C, right? But it is stronger to prove things in a priori stronger in SL2C. Now, I mean, notice if these guys are conjugate in GL2C, they are automatically conjugate in SL2C because you see when one conjugates, let's say A times SL2R times A inverse, right? The thing is, the determinant of this one is the inverse of the determinant of this one, right? So one can just take that conjugation, right? Take this conjugation and divide A by its determinant, and this doesn't change. That's the point. So showing that two subgroups of SL2C are conjugate in SL2C. So given two subgroups of SL2C, if one can prove that they are conjugate in GL2C, then one automatically can deduce that they are conjugate in SL2C, in the smaller group. And that's what we are going to do. So what I just said is I pretty much told you this why. And what am I going to do? Well, I already know a matrix that somehow, at least I know that it partially does the job, right? Because it takes U bijectively onto D, right? Okay, so that's what I'm going to show, that the conjugation by that matrix, by the Cayley matrix, is that matrix conjugates both groups. Even though it doesn't have determinant 1, right? But I already told you why it doesn't matter. Okay, now we compute the inverse, right, of the Cayley matrix, right? That's very easy to compute. I mean, you take the transpose of cofactors, right, and divide by the determinant. So here, when we compute, here in the denominator, you are always seeing the determinant of the Cayley matrix, which is 2i, right? It's I plus I, right? And the cofactors, like for instance here, you have I. Here you have 1, right? Here you have 1, but you transpose, right? And with a minus sign, right? Because it by definition of the cofactor, so you have minus 1. So this minus 1 is minus this guy. And similarly, here you obtain minus I, but with a minus sign is I, and then transpose, you put it here. Okay. Right, I mean, and then of course here this I cancel, and then here you compute the inverse, blah, blah, blah. So you obtain this, right? And then when you take a matrix in SL2R and you conjugate, well, here this 1/2, you can put it here. Now the determinant of this guy is 1, right? Because the determinant of this guy is, well, the determinant of this cancels with this, and so the determinant is just the determinant of this guy, which is 1, right? So this is going to be important at the end. Remember that this has determinant 1. Now, and the rest is compute, right? Computing. Right. So this times this, this times this, you see it very easily, right? Not much to explain. And then this times this, right? Not much to explain. We all know how to do that computation. And then write things conveniently, right? So this I write it like this, right? I mean, I times minus I is 1. Okay, and then I, and then it's beta minus gamma. Okay. Now this one as well. I mean, it's minus I times minus I is minus 1, so it's alpha minus delta, and then plus I times minus beta minus gamma. Okay. Oops, I'm sorry. Just 1 second, I'm sorry. Okay, sorry about that. Okay, right, and then the same thing, right? I mean, you do it right, and then after writing things like conveniently, you see that like compare this one to this one, right? The difference is that what accompanies I is you see this is minus this, right? So these ones are conjugate, and similarly, this one is minus this one, and that's all the difference between this and this. So they are conjugate, right? So right, so we have let's say if this was A, this is A conjugate, and if this is B, this is B conjugate. Right, and the determinant is 1, so the norm square of this one minus the norm square of this one, well, of course, after multiplying with 1/2, is 1, right? So this matrix definitely is in SU11, right? Because we already knew that this one had determinant 1. Okay, so this means that we have shown this containment, this inclusion. And now for the other inclusion, well, it suffices to show that every matrix here is of the desired form, conjugate to someone here, which is the same as saying that when you conjugate this guy, but now, passing this to the left and this to the right with the inverses, you obtain someone in SL2R. Okay, let's do that, right? So now this one inverse appears on the left, and this one without the inverse now appears on the right. And here we put an element of SU11. So it has determinant 1, and the entries, the second row is determined by the first row, as we said before. And we start computing, right? This inverse is here, okay, and then we perform first this, and then this. We arrive at something here, and then we write it in a convenient way, right? For instance, this guy, we of course can write it as Z plus W plus the conjugate. This one we can write it as IZ plus IW plus this conjugate, right? I mean, when you conjugate this one, conjugation opens sums and products, so that's why you have minus I here and a minus I here. Okay, and similarly this and this, right? So what we arrive is that each of the entries of the result, even after you multiply with this real scalar, they are all of the form sum1 plus its conjugate. So they are all reals, right? So because they are 2 times the real part of something. Right. So this is actually a matrix with real entries, and it has determinant 1 because this had determinant 1, right? So it's in SL2R. And that's going to be it for today. Okay, so this was a short class.